In March 2022, a language model with 70 billion parameters was tested against one with 280 billion.
4 times bigger.
4 times bigger. And the smaller one won. Not narrowly, and not on a single cherry-picked task. The paper's word is uniformly.
Here's the part that matters, though. Those two models cost the same to train.
Say that again?
Same compute budget. Same lab. Roughly the same underlying method. One team spent that budget on parameters. The other took the identical budget, spent it differently, and got a better model out the other end.
So nothing improved about the hardware.
Nothing at all. No new chip, no new memory, no new interconnect. For 5 episodes, this series has been about machines making ideas possible. This time, the correction ran the other way. And it wasn't even a new idea. It was arithmetic. A claim about how a budget should have been divided in the first place.
And the field had been dividing it wrong.
For about 2 years, with the best available advice telling it to.
This is episode 6. Bigger stopped meaning better, and what it takes to keep scaling moved somewhere almost nobody was looking.
Quick note, this is education, not advice of any kind. AI moves fast, so treat it as a map, not gospel, and go try it yourself. Let's put this on the loop, because episode 6 set an odd point on it.
The loop being, an idea appears. Hardware decides whether it can be tested, results either validate it or bury it. Useful results attract money, money buys better hardware, and bigger ideas become testable.
Right? And episode 5 is where the direction flipped. After 2012, training compute detached from the general-purpose trend line, and by the end, the method was specifying the silicon. Google building TPUs, Nvidia adding tensor cores.
So the natural next chapter is, and then they made it bigger still.
That's what everyone expected. It's not what happened. What happened is that somebody went back and checked the arithmetic on the previous 2 years of spending.
And this is the strange part on the loop, because it's not step 1 and it's not step 5.
It's not a new idea, and it's not new hardware. It's a correction to allocation, to how a fixed budget gets divided between 2 things you can buy with it. And allocation errors are invisible while you're making them. Every model was getting better. Every result was going the right way.
You can be wrong and still be improving.
You can be wrong and still be improving. That's the whole episode, really. Progress is not the same thing as efficiency, and it's very easy to mistake one for the other when the numbers keep going up.
So, where did the 2 years of advice come from?
A 2020 paper from OpenAI, Kaplan and colleagues called Scaling Laws for Neural Language Models. And I want to be careful here because this paper gets treated as the villain of the story, and it really isn't.
What did it actually say?
It found that model performance follows remarkably clean power laws across more than 7 orders of magnitude. And then it gave practical advice about spending a compute budget. Their words, larger models are significantly more sample efficient, such that optimally compute efficient training involves training very large models on a relatively modest amount of data and stopping significantly before convergence.
Very large models. Relatively modest data.
And the numbers behind that were specific. If your compute budget goes up by a factor of 10, the recommendation was to grow the model about 5.5 times, and the training data only about 1.8 times.
So almost everything goes into parameters.
Almost everything goes into parameters. And if you're wondering why the years after 2020 produced this parade of ever larger models with headline parameter counts, that's why. It wasn't vanity. It was the best evidenced advice in the field from a careful paper, and everyone followed it.
So what went wrong?
Nothing went wrong. Exactly. Kaplan's team measured something slightly different from what everyone assumed. Their models were, in their own words, stopped significantly before convergence, and the learning rate schedules differed from what later work used. Change those conditions and the fitted numbers move. Same question, different regime. That's the fair way to say it, and I'd rather be fair than dramatic.
So in 2022, DeepMind goes back and asks the question again.
They train over 400 models, from 70 million parameters up past 16 billion on 5 billion to 500 billion tokens. And they fit the curve properly, running to convergence.
400 models just to answer a question about how to spend money.
Which tells you how much money was at stake. If you're about to commit a 9-figure training run, spending a fraction of that working out the correct ratio first is obviously worth it. The strange thing is that nobody had done it at that scale before.
And the answer comes out different.
The answer comes out very different. There's sentence, and this is the one to remember. For compute optimal training, The model size and the number of training tokens should be scaled equally. For every doubling of model size, the number of training tokens should also be doubled.
Equally. Not 5.5 to 1.8.
1 to 1. Double the model. Double the data. And they put a number on how badly this had been missed. We find that current large language models are significantly undertrained.
Undertrained, not oversized.
That's the precise word, and it's doing a lot of work. The problem wasn't that the models were too big in some absolute sense. It's that they've been fed too little for their size.
Give me the scale of too little.
Most of the large models of that era were trained on something in the region of 300 billion tokens, more or less regardless of how big they were. Gopher, at 280 billion parameters, got roughly that. So as models grew from 1 billion to 10 to 100 to 280, the amount they read stayed put.
The models got bigger and the education stayed the same length.
That's a good way to put it. And Chinchilla's claim is that if you doubled the reading alongside the size, you'd have got a much better model for the same money.
And then they proved it.
They took the exact compute budget used to train Gopher and spin it the way their curve said to. That gave them a 70 billion parameter model trained on 1.4 trillion tokens. They called it Chinchilla.
4 times smaller.
4 times smaller, 4 times more data. Same bill. And it uniformly and significantly outperforms Gopher, GPT-3, Jurassic 1, and Megatron Turing NLG. On the MMLU benchmark, it reached 67.5%, more than 7 points better than Gopher.
And that list includes a model of 530 billion parameters.
Megatron Turing, more than 7 times Chinchilla's size.
Okay, I want to slow down because this result gets repeated wrongly constantly.
It really does. And the wrong version is Chinchilla proved that bigger models are worse. It proved nothing of the sort.
So what's the precise claim?
The precise claim is bounded by a condition. For a fixed compute budget, the field had been buying too many parameters and too few tokens. That's it. That's the finding.
And what doesn't follow from it?
3 things. First, it doesn't say a bigger model can't beat Chinchilla. It absolutely can. It just needs proportionally more data to do it. Second, it doesn't say scale has stopped working. And third, it doesn't say the enormous models were pointless. They were inefficient for what they cost, which is a different accusation.
So the one-sentence version is...
Bigger isn't worse. Bigger is wasteful if you don't also feed it proportionally more. And the reason to be careful about that is that the sloppy version of the result would have told people to stop scaling, which would have been expensively wrong. Because what actually happened next was that models kept getting better, using exactly the loophole the sloppy version misses.
There's a part of this story I didn't know until recently.
The part where Chinchilla itself turned out to need a correction.
Tell it.
In 2024, a team at Epic AI, Basiroglu, Erdl, Barnett, and Yu, published a paper called Chinchilla Scaling, a Replication Attempt. They tried to reproduce the original fit, and they found 2 concrete problems.
Concrete meaning what?
Meaning specific and checkable. The first is a rounding error. One of the exponents in the published formula was printed as 0.28. The actual fitted value, sitting in the comments of the paper's own source file, is about 0.2849, and that rounding introduces a bias of roughly 13% at a typical dataset size.
From 2 decimal places.
From 2 decimal places. The second problem is subtler. Their optimizer was terminating early. And we know because, this is the part I like, the original authors confirmed it. They'd averaged a loss value across data points where they should have summed it, and the resulting scale caused the fit to stop before it had properly converged.
Though the paper about models being stopped too early had a fitting procedure that stopped too early.
I'm not going to pretend that isn't funny. There's a third finding. The confidence intervals in the original were implausibly narrow. The replication team calculated you'd need something like 600,000 training runs to legitimately report intervals that tight.
So is Chinchilla wrong?
No. And this is why I wanted to include it. The headline survives. The rule of thumb, roughly 20 tokens per parameter, is consistent with the corrected numbers. What doesn't survive is the precise formula from one of their 3 estimation approaches.
Last episode opened with OpenAI correcting its own misquote of Moore's law.
And this is that 1 layer deeper. A correction that itself needed correcting, acknowledged by the people who made it, with the central claim still standing. That's not a scandal. That's what the process looks like when it's working.
So everyone adopts Chinchilla ratios and we're done.
For about a year. And then the field deliberately, openly, and with stated reasons, went and did something else.
Which was?
Training small models for far, far longer than Chinchilla says is efficient. And the clearest statement of why is in the first Llama paper from Meta in February 2023. They say it outright. This objective disregards the inference budget, which becomes critical when serving a language model at scale.
Inference budget, meaning the cost of actually running the thing.
Right. And then the key sentence, given a target level of performance, the preferred model is not the fastest to train, but the fastest at inference. And although it may be cheaper to train a large model to reach a certain level of performance, a smaller one trained longer will ultimately be cheaper at inference.
A smaller one trained longer.
They even give the example. Chinchilla's rule says a 10 billion parameter model wants about 200 billion tokens. Their observation, we find that the performance of a 7B model continues to improve even after 1T tokens.
5 times past the recommendation and still climbing.
And that was 2023. By Llama 3 in 2024, Meta stated the principle outright. We also train our smaller models for much longer than is compute optimal. The resulting models perform better than compute optimal models at the same inference budget.
So it stopped being a workaround and became policy.
It became this stated design philosophy. And the 8 billion parameter model in that generation was trained by Meta's own published figure on over 15 trillion tokens.
Put that in Chinchilla terms for me.
Chinchilla optimal for an 8 billion model is roughly 160 billion tokens. Over 15 trillion is on the order of 1900 tokens per parameter. That's our arithmetic, not theirs, but it's close to 100 times past compute optimal.
100 times past the efficient point on purpose.
On purpose, documented, and with a perfectly good reason.
So which is it? Was Chinchilla right or not?
Chinchilla was right about the question it asked. The question just stopped being the important one.
Unpack that.
Compute optimal training minimizes one thing, the loss you get for a fixed training budget. That's real and useful. But a model that ships has 2 costs, and they behave completely differently. You pay training once. You pay inference every single time anyone uses it. If your model serves millions of requests a day for 2 years, the training cost stops being the number that matters. It can become a rounding error.
So the optimum moves.
The optimum moves because the thing you're optimizing changed, and nothing was refuted. Chinchilla's mathematics is intact. Somebody just pointed at the objective function and said, that's not the one we care about anymore.
Which is a genuinely different kind of correction from the first one.
Completely. The first said your answer is wrong. The second said your question is wrong. And that kind is much harder to spot, because everything about the work can be impeccable, and it still won't help you.
And once you're optimizing for inference,
you run straight into a wall that had nothing to do with any of this. A physical one.
So let's look at what a model is doing when it answers you.
It generates 1 token at a time. Call it roughly a word. And to produce each token, it runs a forward pass through the network. Every layer, in order.
And a forward pass needs the weights.
A forward pass needs all of the weights. Every parameter has to travel from memory into the part of the chip that does the arithmetic.
So how much is that?
Let's do it with the Chinchilla-sized model, 70 billion parameters. In 16-bit precision, each parameter is 2 bytes. 70 billion times 2 is 140 billion bytes.
140 gigabytes.
140 gigabytes of data movement. And here's the thing people find hard to believe. That's not for the whole answer. That's for 1 token. The next one reads all 140 gigabytes again. A 300-word reply moves something on the order of 40 to 50 terabytes through the memory system.
And the actual arithmetic on those numbers?
Almost trivial by comparison. Modern accelerators can do vastly more calculation per second than the memory system can feed them. The chip isn't struggling to compute, it's waiting for data to show up. And the ratio is close to the worst it can be. You load a weight, use it about twice, throw it away, and load the next one. These accelerators were designed for workloads with heavy reuse. Training looks like that. Generation doesn't, and generation is where essentially all the real usage lies.
I want to put a caveat on that because the number is dramatic, and dramatic numbers get repeated badly.
Please, because there are 3 ways to overstate this.
First one.
The 140 gigabytes per token is true when you're generating 1 response at a time. Real serving systems batch, dozens or hundreds of requests together, and the weights get read once for the whole batch. With 64 sequences running together, it's closer to 2 gigabytes per token per user. Still enormous, not 140.
Second,
This shape only applies to generation. When the model first reads your prompt, it processes those tokens in parallel, and that phase is limited by computation, not memory. Two different regimes inside the same request.
and the third.
At long context lengths, a different thing takes over, the key value cache, holding intermediate results for every token so far. On a long conversation, that cache can get bigger than the model's weights. Tens of gigabytes for a single conversation on a 70 billion model.
So, the honest version is,
At the limit of one response at a time, every new token means reading all 140 gigabytes. Real systems serve many users at once, which spreads that cost. But the shape of the problem doesn't change. The limit isn't how fast the chip can calculate, it's how fast it can be fed.
and that has a name.
The workload is memory bandwidth bound, meaning performance is set by how many bytes per second you can move, not by how many operations per second you can perform.
Which inverts the thing everybody assumes about these chips.
Completely. We talk about accelerators and flops, floating point operations per second, because that's the number on the box. But for the generation phase of a large model, the flops are not the constraint. You could double them and get almost nothing.
How long has this been coming?
Decades, and not because of AI. The gap between how fast processors compute and how fast memory delivers has been widening since the 1990s. It has a name, the memory wall, and it's older than most of the field.
But AI hit it from an unusual direction.
From a direction that makes it unusually painful. Most workloads have some locality. They reuse a working set that fits in cache. Generating a token has almost none. You touch every weight once and move on.
So, caches don't save you.
Caches barely help, which means the only thing that helps is making the main memory itself faster and wider. And that's an extremely physical problem, because moving a byte costs energy roughly in proportion to how far you move it. At this scale, that's not a detail. It's most of the power budget.
So, the electricity bill is largely a transport bill.
A surprising share of it, which reframes the problem. If most of your energy goes into moving data rather than computing on it, the productive move isn't a faster arithmetic unit. It's shortening the distance.
So, what does the industry actually do about it?
Two things, and they're both about geometry rather than cleverness.
Start with the first.
Stop putting memory far away. Conventional memory sits in modules some distance from the processor, and every millimeter costs you time and power. So instead, take the memory chips, stack them vertically into a tower, drill connections straight down through the silicon, and put that tower right next to the logic die. That's high bandwidth memory, HBM.
And stacking is what buys the bandwidth?
Stacking plus width. A conventional memory interface is relatively narrow and very fast. HBM goes the other way, enormously wide, at a more modest clock. HBM3 and HBM3E run a 1024-bit interface per stack. And the newest generation, HBM4, doubles that to 2048 bits.
They widened the road rather than raising the speed limit.
That's exactly it. And it's the single clearest signal of what the industry now believes the problem is.
Is stacking hard?
Very. You're bonding memory dies on top of each other and running vertical connections straight through the silicon. Yields get harder with every layer you add, because a defect anywhere in the tower can cost you the whole stack. And then there's heat. The layer at the bottom is now underneath several other layers, all generating warmth, with nowhere convenient for it to escape.
You've buried the part that needs cooling.
Which is one reason HBM is expensive, and one reason only a handful of companies in the world can make it.
And the second thing?
Packaging, which sounds like the least glamorous word in semiconductors, and is currently one of the most important. You can't just place HBM stacks next to a processor on an ordinary circuit board. The connections are far too many and too fine. You need a piece of silicon underneath acting as a bridge. At TSMC, that's called CoWoS, chip on wafer on substrate.
And that's a constraint?
It's the constraint at times, not the transistors, the packaging. There have been long stretches where the thing limiting how many AI accelerators existed in the world was not the ability to make chips, but the ability to package them next to their memory.
While we're here, there's something about HBM4 I didn't expect.
The base die. In the earlier generations, the chip at the bottom of the stack was essentially plumbing, a passive layer that routed signals. In HBM4, it becomes an active logic chip, memory controller, error correction, the high-speed interface, built on an advanced logic process and fabricated by a foundry.
So the memory now contains a logic chip made by TSMC.
Which is the cleanest proof I know of the thing this whole episode is about. The categories dissolved. It's not the processor company and the memory company anymore. The memory has a co-designed logic die inside it, made on a leading-edge node.
And that changes who can buy it.
Completely. You can't order generic HBM4 off a shelf because it's partner-specific and co-designed, which is part of why the shortage is structural rather than a passing squeeze.
So stacking and packaging is the answer. Does it keep working?
Here's where 2026 got interesting. Because that answer has a limit too, and we just found it.
Go on.
Nvidia announced a part called Rubin Ultra. 4 compute dies, each near the largest size you can print, plus 16 stacks of the newest memory, about a terabyte of high-bandwidth memory in a single package. It would have been the first terabyte-class AI accelerator.
That's a big jump from 288 gigabytes.
Enormous jump. And about 3 months after it was announced, that design was reportedly abandoned.
Why?
Because the package bends.
Sorry, bends?
Physically warps. When you put more than 3,400 square millimeters of silicon onto one substrate, and the different materials expand at different rates as things heat up, the whole assembly deforms. And when it deforms, dies lose electrical contact and your yields collapse.
So this isn't a cost problem or a supply problem.
It's a materials problem. 2 things bolted together that expand by different amounts. The packaging generation that would fix it, putting these on panels instead of substrates, isn't in high-volume production until roughly 2028 or 2029.
So what happened to the product?
It wasn't scrapped outright, and I want to be precise here because the shorthand people use is wrong. What was reportedly abandoned is the 4-die configuration. It's been replaced with a 2-die design, half the compute dies, half the memory stacks.
Which lands the memory where?
Around 384 gigabytes on the most commonly modeled configuration. And the final specification genuinely isn't locked as we speak. Reported configurations run from under 200 gigabytes up to that figure, depending on how tall the memory stacks end up.
So measure it against what was promised rather than against today.
That's the honest comparison, and it's still brutal. The announced part was about a terabyte. What's likely to arrive is somewhere around a third of that. The terabyte didn't survive contact with the physics.
And I should say, none of this is confirmed by the company.
None of it. Nvidia hasn't announced a cancellation, and their public line is that they continually optimize. This is consistent reporting across a lot of outlets, plus supply chain analysis, and I'd rather label it that way than pretend it's settled. It's also worth saying that this part of the story moves fast. Specifications in this industry change between an announcement and a shipment, and by the time you watch this, the number may have moved again. What won't have moved is the reason. You cannot put unlimited silicon on one substrate and expect it to stay flat.
There's a second thing that happened here too.
And it's my favorite detail in this episode, because it pays off something we said earlier. Remember the caveat, that reading your prompt is compute bound, and generating the reply is memory bandwidth bound? 2 different phases with 2 different bottlenecks?
The distinction I made you spell out.
Nvidia built a product around that distinction. There's a Rubin variant that drops high bandwidth memory entirely for one phase and uses ordinary graphics memory instead, 128 gigabytes of it at roughly a fifth of the memory cost, for about 60% of the performance on that specific job.
Because the prefill phase doesn't need the expensive memory.
It doesn't need it. It's compute bound. So you'd be paying an enormous premium for bandwidth you can't use. Split the machine by phase, and give each phase the memory it actually needs.
So a distinction that was a footnote in our explanation
is now a stock-keeping unit. That's how you know an idea has really landed. It stops being pedagogy and turns into a product you can buy.
Okay, so if one chip can't hold more, what's left?
Connect more chips. And connect them so tightly that the model can't tell they're separate.
Which is where the numbers get genuinely startling.
Let me give you 2, side by side, over the same 4 years. From the H100 in 2022 to Rubin now, the memory on a single GPU went from 80 gig to 288, 3.6 times.
And the other number?
The memory inside a single tightly connected group of GPUs, what Nvidia calls an NVLink domain, went from about 640 gigabytes to around 41.5 terabytes.
That's 65 times.
65 times against 3.6. And that's the whole shift in one comparison. The chip barely moved. The room exploded.
How many GPUs are we talking about?
The domain went from 8 Rubin-class GPU packages to 72 to 144 today. The next one on the public roadmap is 576. The one after that is 1,152.
And I want to be careful with that count because I've seen it written differently.
You have, and it's worth 30 seconds. You'll see 72 attached to today's Rubin rack in places. That's counting the trays, where each tray holds one CPU and two GPU packages. Counted as GPU packages, which is what matters for memory, it's 144. Those are the same rack described two ways.
So the unit of scaling stopped being the chip.
The unit of scaling became the domain. And that's not a metaphor. Inside that domain, the model genuinely doesn't see 144 separate accelerators. It sees one computer with tens of terabytes of fast memory.
Why does that matter so much for the models we actually run?
Two reasons, both concrete. Modern large models are often mixtures of experts. Only a fraction of the network activates per token. But tokens have to be routed to wherever those experts live. That's constant all-to-all chatter. And inside the domain, it moves at terabytes per second. Outside it, over the ordinary network, you drop by a large factor and add latency. The second reason is the key value cache we talked about. At long context, it's enormous. And inside a domain, one GPU can read another's cache directly.
So the pressure is to make the domain as big as possible.
As big as you can. And that runs into the next wall, the one nobody outside the industry sees coming.
So what is the wall?
Copper. At the signaling rates these links now run, an electrical signal on a circuit board stays clean for something like 10 to 20 centimeters. After that, it degrades into noise.
10 to 20 centimeters. And the domain is a whole rack.
Multiple racks soon. So you switch to light, which carries more information much further for far less power. Except that plugging optical modules into a switch has its own cost, roughly 25 to 30 watts each. Put 500 of them on one switch, and you're burning 12 to 15 kilowatts on the optics alone before any computing happens.
So what do?
You stop plugging optics in from outside and build them into the package. Co-packaged optics. The laser and the switch chip share a package, and the electrical path collapses from most of a board down to a few millimeters. For its photonics switches, Nvidia's published figure is about 3.5 times better energy efficiency.
Is that shipping or is that a slide?
Shipping. Their photonics switches have been going to selected partners since the middle of this year. But here's the announcement that actually settles the argument. For 2028, Nvidia has said the NVLink fabric itself, the scale-up fabric, the thing that makes those GPUs act like one computer, gets co-packaged optics.
So light moves from between the racks to inside the machine.
Inside the machine. And that's a company saying, in its own product roadmap, that the domain cannot keep growing on copper. You don't redesign your most important interconnect around silicon photonics unless you've run out of alternatives.
And I assume light solves it?
Light is the piece that makes the next size possible. And it's worth stepping back to see the shape of what we've described, because it isn't a story about one thing beating another.
Say what you mean by that.
Every part of this had to grow together. Better arithmetic on the chip, more memory, and much faster access to it. Then a way to make many chips behave as one. Now light, because that's what carries the connection at the size we've reached. None of those replace the others. They're all still there, all still improving, and each one made the next one worth doing.
So it's not memory instead of compute, or optics instead of memory.
Not at all. It's that whichever part is furthest behind at a given moment is the one you notice. And right now, at the frontier, that's how fast you can move data rather than how fast you can compute on it. Give it a few years, and that could easily be somewhere else again. These are engineering problems, and engineering problems get solved.
I want to push back before we close, because this is a tidy story, and tidy stories worry me.
You should push back, and there's a real counter-argument.
Make it.
Most inference in the world today does not run on 144 GPUs. It runs on 1 or 8. And at that scale, the constraint is exactly what we described in the middle of this episode. The memory bandwidth on the chip in front of you. The network is invisible. And more than that, the reason those memory specs are being cut is that high bandwidth memory is scarce and expensive. If memory were abundant, that terabyte part would have shipped.
So memory is still the binding constraint.
For the median deployment, memory is still the binding constraint. And anyone who tells you the story is now purely about networking is selling something.
Can you put a number on that? Because it's expensive is doing a lot of work in that argument.
Here's the one that explains it. High bandwidth memory is now over 40% of all memory industry revenue. from only about 23% of the wafer output. Each bit of it consumes roughly 3 times the manufacturing capacity of ordinary memory.
So it's expensive because it's genuinely hard to make.
Genuinely hard. And capacity takes years to add, which is why a company would rather trim a specification than wait. But I'd be careful about reading that as a permanent ceiling. It's a manufacturing ramp, and manufacturing ramps finish. If memory gets cheaper to make, a lot of what we've described gets easier all at once.
So how do you want to leave it?
Like this. The memory wall binds where most inference actually happens, and the interconnect wall binds at the frontier. The biggest models, the longest contexts, the largest training runs. 2 different regimes, both real and both temporary in the way engineering constraints usually are.
So where does that leave Moore's Law?
Alive but relocated and further than I expected when we started. It stopped being a property of a transistor decades ago. Then it became a property of a chip and its memory. Now the thing that improves generation to generation is a property of a room. The racks, the fabric between them, the light moving through that fabric. Progress you assemble and wire rather than shrink.
And the thing to be uneasy about.
Look at what we've described. A machine specialized around one method, enormous parallel matrix operations. And that specialization now runs all the way out through the memory, the packaging, the fabric, and the optics. It isn't a chip that's committed to this shape anymore. It's a building.
Which is Episode 5's trap. Several levels deeper.
Much deeper. You can replace a chip. Replacing an architecture that's been poured into concrete power contracts and photonics supply chains is a different proposition entirely.
So the question for next time.
Next time? The last one. What comes after large language models? If an idea arrives that doesn't decompose into enormous parallel matrix multiplications, that wants memory arranged differently, or sparsity, or something that looks nothing like a transformer, how does it get a fair test on a machine that's been specialized for something else all the way out to the fiber?
And whether we'd recognize it.
That's the one that keeps me up. Every episode of this series has had a moment where the right idea looked wrong because the machine couldn't run it yet. There is no reason at all to think we've had our last one.
That's a wrap. If this made AI a little clearer, hit subscribe. It helps more curious people find the show. See you next time.